Good afternoon, everyone. My name is Choi Seokwon, undergrad student in physics, Department of Physics at Yonsei University. And also I'm serving as a vice president in QIYA. And today I'm going to present my topic, the future of HHL algorithm through recommendation system models. In this presentation, we'll start by explaining HHL algorithm is, and we are going to talk about examples of HHL algorithm, the recommendation problem. And finally, we conclude with a discussion followed by appendix. And from now on, I'm going to explain what HHL algorithm is, but I'm not going to explain deeply because of limited time. HHL algorithm has given name because Harold Hasidy Lloyd made this algorithm at 2009. This is algorithm to solve linear system of equations, and that is a method to find x when ax equals b. To solve this in a quantum system, we transfer this as a quantum model, and we utilize QPE like as a subroutine and get an exponential speed up from that. And I'm going to introduce example of this as I'm going to explain the usage of example as a recommendation problem. The recommendation problem is about recommendation system. It suggests products to users based on past purchase ratings of products. The recommendation system makes suggestions about products to individual users. By analyzing these patterns, we can approximate the preference metrics from existing data and make predictions for similar users. As an example shown in the PPT, like Netflix, when you add a movie like To Kill a Mockingbird, if you have seen it, the system groups you with some types of similar users. Based on this grouping, you recommend similar movies like the shown in the picture. So our problem is simplified as getting an approximation of the preference metrics and suggest other people who like a same type as a recommendation. The insight of recommendation problem is define a preference matrix T, which is epsilon close to original matrix. And we predict this data. And based on previous studies, approximating in low dimensions will be used. For this, we define T as a M times N matrix, where the entries represent user product preferences. And we produce this data into specific vectors for further analysis. And M represents the number of users, and N represents the number of products elements in that matrix. Just like the projection on the right side of my PPT, you can see that from rank KR space, we extract sigma 1 to space KR only. Like you can see the arrow projection over there. We just extract for the things we are going to use in the recommendation system. Okay, then I'm going to explain the quantum algorithm to use recommendation system. Yeah. In quantum algorithms from prior research, we use the theorem projection onto one sample, AK is close to projection onto one AK. This is where therefore low rank approximation, like I discussed before, can be efficiently achieved using sampling methods underneath my PPT. By defining a samplist matrix AK, which includes some scaled entries from original matrix A, then we can achieve similar results without significant loss of accuracy. The sampling rule enables the first computation by focusing only on relevant elements. Like you can see the one over there, and we just extract what we need for the approximation and amplifying like the blue color at there, like following the sampling rule. And by applying low rank approximation of sample following and the sampling techniques discussed earlier, we can effectively approximate the preference metrics in recommendation systems. The resultant quantum state corresponds to a row of the sampled metrics representing a user's preference, which enables to make accurate recommendations. And from the binary research tree, like state preparation could be done in polylog m and time. This is shown in appendix, and you can see how it works, but I'm not going to explain this because of limited time. Okay, from method of projection, like I discussed later, before, what we need is a projection of sample of single values in the interval. Using HHL algorithm, which solves the system of learning equations, can be used to estimate the single values by performing demapping. Because it estimates the sigma value lies on the interval, like shown there. For projection, the HHL algorithm helps to estimate single values by mapping, and where sigma I was in the specific range. This allows us to project the sample data efficiently, achieving accurate approximation in the polylog m time of a epsilon. You can see the algorithm follows on this diagram, like sampling, rounding the preferential matrix and sampling there, and we can solve the quantum methods using quantum singular value. Okay, to quantum the probability that this algorithm produces a bad recommendation can be calculated using the given formula. So in order to work in practice, there are a threshold defined as epsilon, and this is shown in the previous paper. And we have to define kappa equals 1/3 to work in practice. And therefore, the algorithm runtime could be like, we discussed the polylog m times later before regarding the method of projection. And we just add polylog k. So the total runtime would be poly k polylog m time. By inspiring this, we can think of quantum-inspired algorithm using classical computers. In a quantum-inspired recommendation system, we are going to introduce some methods to, like we sample data and we extracted eigenvalues from there, but we are going to change it in classically. A quantum-inspired approach uses different sampling instead of complex quantum computation. For example, a KFB algorithm approximates the matrix M by sampling rows to N, such that N transpose N is close to M transpose M, and A transpose N span to column space. And a modified version uses the L2 norm sampling based on single values, enabling a probability distribution proportional to the squared probability norm. This gives the probability regarding to the singular value vector, like you can see from the PPT down there. One goes to probability there, like during the graph, and you can see. So in a quantum inspired recommendation system, a sample of S rows a matrix A provides good approximation to A, where D is the best low-rank approximation. And we can apply sampling rules both rows and columns, like just we did in the quantum algorithm, but we are going to sample the data and sample rows and columns. You can see from the diagram over there, you can extract data from sample rows and columns. We following the sampling rules over there, we can make like if the data is million times million, we are going to reduce this as constant times. Like if you get a million time million all the data, we are going to reduce this dimension to constant time, like 5 by 5. So this using this method, we computing this will be very easy. So projection is computed by determining the top k singular vectors. Like we are going to extract and we are going to project in classical way. So U1, U2, UK, so the column space of W, this is spanned into row space using VT, like VT and VT times VT transpose. We can think of approximation project vector like over there. And the probability of failure is about 1/10, and but this takes very much of mathematical methods. But if you want, you can see on the paper. So the total diagram of quantum-inspired algorithm is, you can see like quantum algorithm has you have a same rounding process, but unlike the metric sampling that quantum algorithm has, we have a L2 norm sampling, like the Frobenius norm, and you can get a constant size of sample. Like we tried to reduce the calculation, and we have a classical SVD from there to find the approximation. Unlike the quantum algorithm, just quantum system to find the eigenvalues. Okay, and this is my explanation about algorithm, quantum algorithm and quantum inspired algorithm, and we are going to discuss about this. I don't know. I'm going. I have to explain the quantum inspired algorithm one time, and because it takes only poly k time to rounding, and we get a log mn time to get a method. We just have a polylog k log mn time, and this is only polynomially slower than the quantum algorithm. Regarding quantum computers in practical deviations, you can think that this algorithm works pretty well. Okay, the total runtime of the quantum-inspired algorithm was only poly k log n time, and which was slightly slower than quantum algorithms. This raises us the question: does HHL still offer a quantum advantage? In classical method, the same rounding process is applied to preference metrics, but L norm sampling and classical SVD are used instead. In conclusion, if the entire algorithm can be simulated on classical computers, any problems solved on n-qubit quantum computers can be resolved only within fully n time. This implies PQP equals P space, making quantum computers nearly obsolete. Therefore, while we believe HHL offers exponential speedup in theory, more practical research is needed to validate its real-world utility. This was why I think it ended faster than I expected. This is my presentation. If you have any questions, feel free to ask. 그런 게 이런 방법 말고도 다른 컴퓨터 스파이들은 안 보이세요? 그거는 제가 조사를 잘 못해서 제가 조사한 바로는 네 이렇습니다. 그래서 사실 이렇게 되면 저희가 양자 컴퓨터를 쓸 이유가 없어지죠. 근데 저희는 그렇지 않기 위해서 다른 노력들을 해봐야 되지 않나 또 하는 생각입니다. 네. 네, 그렇게 생각합니다. 네. 말씀하신 게 뭔지 제가 잘 모르겠는데 스파 스페이스 매트릭스가 뭔지 좀 설명해 주시겠어요? 네. 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 그러한 고전 수학 테크닉이기 때문에 퀀텀 인스파이더라고 볼 수 없다라고 말씀하시고 싶은 건데. 네. 그 네. 잘 모르겠습니다. 다른 질문 있으신 분 있나요? 쓰시다면 이쯤 발표 마무리하도록 하겠습니다.